Hello and welcome to this video walkthrough for the OCR Gateway Science Physics Paper 1 from June 2015. This video is split actually into three separate videos. The first video, this one, will be dealing with section A, which is about P1. Turning to page 2 of the paper, it's worth pointing out the equation sheet that you can refer to, and it's also worth pointing out that the first section, P1, is actually the equations that are actually located at the top here, so they should be very easy to find. So we'll be principally using these three equations in this particular section of the paper. Okay, question 1. Look at the advert about double glazing. Buy Evercozy double glazing. Fitting double glazing in your house will save up to 18% on your energy costs. Spend a little and save a lot. Choose Evercozy. Simon has double glazing fitted in his house. He thinks it saves him money. Look at the data. So then we're presented with a table of data, and the key things about it are you've got a 6-year period. First 3 years are without double glazing, and the second 3 years are with, and then the third column on the right just tells you what the annual energy cost is in pounds. And we can see that from the bottom 3 rows, they are generally lower than the costs from before fitting double glazing. So Simon saved some money. Before he fitted double glazing, Simon's average annual energy cost was £1,083. With an 18% saving, the average annual energy cost should be £888. How do Simon's actual annual energy costs from 2012 onwards compare to this figure? So this is what we need to do. It's this comparison that we've got to focus on. So we've got to compare his average annual costs to before 2012 when he didn't have double glazing. And if you do that, if you work out the average of these three numbers, it comes to £920. And obviously that is higher than the expected £888 average cost. So that's what we've got to comment on. So that's your first 2 marks out of the 3, and then the question asks you to suggest reasons for this difference. And they are quite varied. So basically, lots of you got this mark. Sometimes the years are warmer or colder than others. There obviously could be changes in Simon's behaviour. So a lot of you actually pointed out that he could be opening his windows, and that would affect obviously his energy costs. Equally, he could be spending more time at home, or there could be someone else living with him. All that might affect the way that he uses his energy. And then, of course, finally, the cost of energy may just have increased in the last 3 years. Question 2. This question is about energy transfer and how it is used in cooking. A. Steve heats a pan of water on his cooker. Look at the diagram. Okay, so the question asks us to explain how the particles in the aluminium base conduct energy through the bottom of the pan. So many people didn't answer this question very well. What we're concentrating on is just the energy moving through the base of the pan. So it's just conduction. That's all we've got to do is explain how conduction works. We don't have to talk about convection. We just focus on how the heat energy moves through the base of the pan. So it's the classic explanation. You first of all mentioned that the particles in the base gain energy, and that makes them vibrate more. Those vibrations then pass that energy on to the neighbours because they jostle and jiggle and collide with the neighbours, passing on the energy. And don't forget about metals. Metals are good conductors because they contain free electrons. So as well as that mechanism, which would happen in any solid, you also have free electrons that transfer the energy by moving and colliding with the metal ions or atoms. Part 2 of the question then goes on. There is a convection current in the water in the pan. Steve wants to describe the convection current. Look at his description. So here we have the description that Steve says or writes or whatever. The water is heated and it contracts. This makes the water more dense, so it rises. And this is the important part. His description is wrong. Rewrite his description correctly. So that's what we've got to do. We've got to rewrite his description correctly. So we don't have to come up with anything ourselves. We just have to rewrite those two sentences, but change the bits that are wrong. And the bits that are wrong are basically that he's saying that when water is heated, it contracts. And when water contracts, it would make it more dense, but of course that's wrong. If it was rising, it's got to be less dense. And so when we rewrite that, we say the water is heated and it expands, and this makes the water less dense, so it rises. Question 2 then continues. Steve has a combination microwave oven. It can cook food using microwaves or infrared waves. Microwaves and infrared waves cook food in different ways. What is different about the way microwaves and infrared waves heat food? So this is quite a tricky question to get 2 marks anyway. So the key thing to realize is that obviously microwaves are absorbed by water or fat molecules, whereas infrared waves are absorbed by the surface particles of the food. But to get the 2 marks, you had to mention about how that affects the particles of the food. And it's all about absorbing that energy. So microwaves increase the kinetic energy of the water or fat molecules. You could have said it the other way around. You could have said that infrared waves are absorbed on the surface, and infrared waves then increase the kinetic energy of the surface particles. But it didn't matter which way you said it, but you needed to get the 2 marks, you needed to mention how absorbing that energy increases the kinetic energy of the molecules, which is obviously why the food heats up. Then part 2 said, what is similar about the way microwaves and infrared waves heat food? So the key thing is, and quite a few of you got this, both of them transfer energy to the rest of the food. So they cook the rest of the food by transferring that energy through conduction and convection. So that would get you 1 mark. And of course, the other similarity that they have is they're both electromagnetic waves. So they both work in kind of the same way, that they're absorbed by particles and raise their kinetic energy. But of course, the particles that do the absorbing are different because of the different wavelengths. But the fact is that they are both electromagnetic waves would have got you that extra mark. Question 3 is a 6-mark question, and it says, CD players use lasers to read information from a disc. Look at the simplified diagram of the laser and cross-section of part of a disc. So some good information here that will help you. The key thing is that obviously you have a shiny aluminium layer, and that layer has lands and pits, so bumps and hollows from which a laser is going to reflect, and you can see that the laser is reflecting here. So, there's a few pointers as to what you've got to talk about. It then says, describe the properties of a laser beam and explain how information is stored and read from the disk. So I see this as 3 sections. You've got to definitely state what the properties of a laser are. You've got to explain how information is stored on the actual CD. And then the third part, is that you've got to explain how it's read from the disk. Okay, so what I've said is a laser beam is coherent. So its main properties is this idea of coherence. And what coherence means is the light, all the light coming from lasers is in phase and monochromatic. So it has a single frequency. It's all one color. That's what monochromatic means. So those are the properties of the laser that you need to be aware of. So how is the information stored actually on the CD? Well, the clue, there's plenty of information in the question to help you answer this. Information is stored in a pattern of lands and pits. Okay, so you just look at it. You can see that some of the lands are longer than others. Some of the pits are longer than others. So it's that pattern that is coding the information. The laser is reflected from the shiny surface. So we're moving on now to that third part of how then do we read this information. The laser is reflected from the shiny surface of the CD. That's important. And it's that pattern of lands and pits is used to create a digital signal. So all the music, all the different notes and melodies and all the rest of it is coded in a series of dots and dashes, digital signals, and that is in those pits. And it's the way that the light reflects off of those lands and pits that creates that digital signal. The digital signal is then decoded by the CD player, and of course it's transformed back into the music. It then creates an analog electrical signal, and that analog electrical signal is a copy or analog of the original music. Question 4. Look at the diagram of the Earth. An earthquake produces P waves and S waves. Look at the diagram. It shows the initial directions of the P waves and S waves. So here we have our diagram. It gives you a basic structure of the Earth. You've got the core, or the inner core, and the outer core. That's important because you need to know that for later and recognise that there's a inner and outer core. You've then obviously got the mantle, a very thin crust, and we've got our earthquake source here. And all the P waves and S waves are emanating from that source in all directions. And that's the starting point. So the first question says, P waves and S waves are detected by seismometers on the Earth's surface. Each type of wave from the earthquake is detected at different times by seismometers. Which type of wave is received first? Well, the answer to that is the P waves. So this is just a bit of factual recall. P waves are actually received first, but you don't get a mark for that. The mark is for actually explaining your answer. And it's because you need to know that P waves are faster than S waves. Now, one way of remembering this is that you can think of P as standing as for primary and S for secondary. So primary gets to you first, secondary gets to you second. Okay, and it's a good way of remembering. But the key thing is you've got to realise that it's because P waves are travelling faster than S waves. Remember, P waves are longitudinal waves and S waves are transverse waves, which explains a lot of their properties. So moving on, part B, scientists take measurements of P waves and S waves using seismometers. After an earthquake, scientists can work out the exact position of the earthquakes using these measurements. Suggest how they do this. Well, it's down to the fact that you do have this lag time, this difference in time between the P wave hitting or reaching you and the S wave reaching you. So it's that difference in time that can be used to calculate the distance travelled. So this statement here actually gets you 2 marks. Connecting the idea that the difference in time can be used to calculate how far the P wave and the S waves have travelled. Okay, and then to get you your extra mark, what you then do is you then obviously have these seismometers at different points on the Earth. They will all receive the same information, all be slightly different, and what you can do is triangulate your data to locate the epicenter of the earthquake. Okay, so that's for your third mark. Sorry, for your second mark. And then part C, S waves do not travel through the Earth's inner core. Explain why. Well, they don't travel through the Earth's inner core because they don't travel through the Earth's outer core. So S waves cannot pass through the outer core because it is made from liquid. So remember, S waves are transverse. That means that they cannot pass through liquids because the liquids will not pass on that perpendicular vibration. So remember, transverse waves, the vibration is perpendicular to the direction of the wave, and in liquids you've got no connection between the material that's vibrating, and so if it's going to go sideways, perpendicular to the wave, then it's just not going to work. And the final part of this question, it says P waves and S waves are different. P waves are longitudinal and S waves are transverse. Look at the diagram of a model of an S wave made from a slinky spring. So the key thing about this is that you've got some data on it. you've got two numbers. You've got this number here and this number here. So we need to know what they mean and what they're showing us. Okay, so let's have a look at the rest of the question. The wave is made by moving the spring up and down with a frequency of 1.2 Hertz. Look at the diagram, calculate the speed of the wave. Well, going back to page 2, you can obviously get the equation for this. So the equation for calculating the speed of the wave is wave speed is equal to frequency times lambda, or frequency times wavelength. So we know the frequency because that's in the question, but we need to find the wavelength. So a lot of you went for this figure here, but there's a problem, because a wavelength, as I've indicated on the diagram, is actually the distance between two adjacent or consecutive repeated points on a wave. So the easiest thing to do is it's the distance between two crests. Okay, this crest and this crest. But your measurement here is actually the distance between this crest and this crest, which is actually two wavelengths, twice the distance. So the number that we want to use is actually half of 1.6 meters, which is 0.8. And then going back to our question, you can see then you just stick it in. 1.2 times 0.8 is equal to 0.96. Okay, and that gets you the 2 marks. So if you did use the 1.6 meters, you would have got 1 mark for using the correct, choosing the correct formula, putting it in the right place, selecting the right number, I suppose, from the actual diagram. But of course, you wouldn't get 2 marks because, of course, you didn't. You needed to halve the 1.6 to get the actual wavelength. And then that leads us on to amplitude. So let's go back to our diagram. Now, amplitude is the height above the resting position. So the resting position is going to be down the middle here. So if there's no wave passing through a slinky, all the coils would sit on that line. So again, it's just recognizing that the amplitude is not the height from the top to the bottom of the wave, but it's actually the height above or below this resting position. So again, this 0.22 meters is the wrong value. Okay, so we actually want half of that value. So if we go back to the question, what is the amplitude of the wave? Well, it's not 0.22 meters, it's actually 0.11 meters, and you should have written that answer there. So that's the end of the section A of the June 2015 exam, module 1 exam. So the second section will be continued in another video.